We're here to talk about gradient boosting tonight. If I can impose, could anyone who's used this before raise their hands? Coworkers, no cheating? Awesome, we got 4 or 5 people in the audience. Hopefully you all can find a business use case for this after we're done, because I think it's a really interesting algorithm. So gradient boosting is a boosted ensemble of decision trees fitted in a stage-wise forward fashion to minimize the loss, which is a bunch of words that are somewhat complex. But what it really means is it's a sum of decision trees where each tree corrects the errors, or attempts to correct the errors of the previous union of trees. So in that sense, it's fundamentally a very different algorithm than random forests, because random forest is all going out and independently doing its own thing and then having some voting or weighted combination at the end. And this is not really the same at all. So in a practical sense, my boss always wants me to talk about why should anyone use this or why should anyone care. So I have some experience working on very large advertising data sets where very large runs roughly in the petabyte range. So even if you very, very heavily sample, you're still looking at millions of rows and thousands to tens of thousands of columns. And what we found is that we could achieve a significant lift over linear models. And what we want to do with this is basically take our set of cookies or device IDs or whatever it may be and rank them for an advertising campaign, compute an expected lift to some depth into our ranking, and then choose that as the group of cookies or identifiers or what have you that we're going to advertise to. So the thing about this is that if we can improve that ranking or improve our lift calculations, this goes directly to the company's bottom line. That's either increased conversions, decreased ad spend, and or happier clients, or all of the above. And the way you're graded on these sort of things is you're graded on a return on ad spend. So all your clients are basically giving you some budget, and they're letting you make advertising decisions, and then they're deciding whether they're going to re-up with you next quarter based on this quarter, perhaps this month's returns. So you need to get it at least approximately right. And so as compared to linear models, what gradient boosting will allow you to do is, in some sense, somewhat automatically build, in a greedy fashion, a series of higher order interaction terms. So the example I really like is that generally young people in college don't have a ton of money to spend, but if you see young people in college on an iOS user agent, that does tend to mean they have quite a bit of money to spend for the right advertiser. And I understand that you could probably have a human think of that, but one of the things that GBM really does for you is it gives you this sort of greedy search, so it can augment the human analyst search through this giant set of feature combinations that exist in your data. And of course, it's a polynomial growth, so you're going to be unable to, you're going to have a hard time doing that by hand. And so anytime you can find a tool that will help the analyst do these searches, it's valuable. Now, one of the things that we did discover is it's painful to get this to run in R. These are not fast models to build, and particularly when you toss a lot of data in, it's relatively slow. So we did have to do some significant downsampling, and we knew that that was bad. So if we're willing to wait, we can discover better models without downsampling, but you need something like at minimum a 1-week turnaround time on these in order to make new advertising decisions, if for no other reason than cookies churn. So you need to constantly be refreshing your model to account for new cookies and new interactions. So the other products that I've worked on are demographics, and the thing about demographics is it's very self-correlated. So younger people go to college, older people make more money. You're going to have trouble if your models expect nice, independent, explanatory variables. And again, this is something that GBM will be able to help you with. And it can pick up on 3 and 4 deep feature products. So, you know, people who visit car enthusiast forums, you may think make good advertising targets for luxury models, but they don't, because a lot of people just go and like to look at these cars. So if you're a car person, you probably go to, I don't know, BMW or Mercedes websites and just look at these cars, even though you're not going to buy a $100,000 or $200,000 S-Series or what have you. But if you can find the people who visit the car enthusiast forums and visit certain types of review sites in some time bound, those people are shopping. And luxury car segments are a very valuable target category for marketers, either because BMW wants buyers or they want to poach each other. So in a more theoretical sense, gradient boosting is a multi-purpose classification and regression tool. And I mentioned it performs variable selection during the fitting process, and it's also nicely robust to highly collinear explanatory variables. As opposed to GLM, you can do all these things in GLM, but backwards forwards, at least in my experience, tends to be somewhat unstable. So GBM will do interaction search to a specified depth in a greedy fashion. Thank you, Cliff. And it will capture nonlinearities in the data without hand feature engineering. So another example is airline on-time performance. GBM will capture sort of an unfortunate change in 2001 without having to have an analyst sort of go in, think about the problem, understand it, and hand code it. Another reason to use GBM is it'll cleanly handle missing data, which is a known pain point for any of your general linear models. You're either going to drop those rows, perform some sort of imputation, lose the columns, do a number of things, but GBM handles NAs and GLM won't without a bunch of pain. GBM will also sort of naturally handle unscaled data. So if you're using GLM, ideally it will handle completely unscaled data, though in a practical world, your matrices will have issues in computations. But again, if you apply L1 or L2 penalties, those are nothing like unscaled. And so if you have variables measured in sort of different units or different order of magnitude units, L1 and L2 errors will be very problematic. Gradient boosting will also handle ordinal data, so something like an ordered factor, if you know what that is. So if you have, you know, income categories 10 to 20, 20 to 40, 40 to 100, or et cetera. Again, recall that GLM is a linear model, so the assumption is that +1 of a dependent variable creates +1 of the corresponding beta effect either in your dependent variable or in the link function. Sorry, I think I said that wrong. +1 of the explanatory variable will create a corresponding plus beta k in your dependent variable. And the problem with an ordinal is what should the distances between neighboring or non-neighboring levels be? GLM, because it's a tree-based thing, will handle this in a very natural way for you. And GLM certainly has a number of tools that you can use to discover this, but they require a bunch of fiddling, and GBM can just handle it. Finally, it's relatively insensitive to long-tail distributions and outliers, and it also handles differently scaled data very nicely. So on the right data set, GBM classification will outperform both GLM and random forests, and it demonstrates good performance on various classification problems. I went trolling through the internet. If you look at the Kaggle forums, for example, this will be one of the standard tools that you will get told to apply first when you go enter any of the competitions. And there's a couple people who have been very successful. The one I like is in the KDD Cup in 2013. 3 of the top 4 teams used it. And one of the winning teams found that they could get very good results with GBM alone and nothing else. But they did point out that the main disadvantage of gradient boosting is that it's slow. So they were using only 300 trees. So here is, so you can get some intuition about what it's doing. On the inside, it's a tree learner, and then we're taking a whole bunch of trees and weighting them in a very particular sense. So what you're seeing here is GBM after only one iteration, so only one tree. And if you look on the left, I built this function, which is certainly nonlinear, although if you were lucky enough to directly observe it, you could imagine fitting it with a spline or a polynomial. In the middle, I have one pass, and so what you can see is that your explanatory data is being cut up into chunks, and you have 6 nodes here, and within each node, you're predicting a constant value. And on the right, you can see the residuals. Now, the thing you should note is that because I have a shrinkage thing, my prediction is on a different scale. So it's a very slow-growing sort of thing. So here you can see the same view on the same scale. The predictions have barely moved from where they started. But if you fast forward from 1 tree to 20 trees, you'll start to see it move. 30 trees, 100 trees, it's starting to pick up on what's going on. And around 300 trees, we have a pretty good set of predictions. The other thing you'll notice is that you're clicking through. The residuals are basically falling to something around 0. And so what you can see from that is these tree-based algorithms are carving your data up into different nodes, into different chunks, and they're essentially building different predictors for each of these chunks. And the bigger residuals get a stronger weight. So briefly, the algorithm, you're gonna, for a classification problem, for example, you're gonna normalize your data. All of this is building regression trees, which is the central piece of this algorithm. And then we cleverly compute weights for the outputs and wash, rinse, repeat. And as Cliff is going to tell you, this is interesting not only because I think you should have a sense of what a regression tree does, because it's the core of this algorithm, but because that's where the time goes. Everything else is a tiny little bit of computation around building regression trees. And if we could quickly walk through what a regression tree actually is, imagine I have this bag and I have some residuals, and on the first row I have my x's. Now the thing you should notice is I can only split when the x variable changes. So I have three opportunities to split: 1 to 2, 2 to 3, and 3 to 4. So this is sort of a view of what a regression tree is actually doing. It's carving it up into different pieces, left to right. It's sweeping over my potential cuts, and it's attempting to minimize a squared error over the residuals. So 1's on the left, 1's and 2's, 3 and 4's on the right, 1, 2, and 3, 4 on the right. And what it's finding, at least in this case, is that the minimal error is carving out 1 on its own, and everything else to the right available for a future pass. Similarly, what a regression tree is really doing here is it's carving up a pair of variables into sort of rectangles with divisions orthogonal to the axes. So there's a direct correspondence between the tree on the left and the division of space on the right. And then within each one of these 1, 2, 3, and 4 units of space on the right, it's building individual models based on the likelihood that you chose when you ran the model. Now, as much as I do like GBM, there's some serious pain points. It's slow to fit, and it's slow to predict. This is basically unsurprising because you're doing this sort of greedy search over some combinatorial explosion of an optimization problem. Particularly if you're willing to let there be fifth order interactions, you have something like the power of the number of explanatory variables you have to the 5th power, which is quickly enormous. It has severe data size limitations. You're often going to have to do downsampling, and of course the fear when you're downsampling is that you're throwing away data that otherwise would improve your model. Many implementations are single-threaded, so it kind of sucks to buy a very nice 32-core computer and watch one core sit there and work and the other 31 sit and spin while you're waiting for your model output. Finally, the parameters are relatively difficult to understand. So things like interaction depths, like how many sets of variables do you consider, are relatively straightforward, but the rest of them, what's going to work well for you, is going to be very data dependent, and you're probably just going to have to go look and do some sort of brute force search and measure the performance of your model over this space. Of course, with some ability to trade off the amount of time versus the quality and improvement in the model results, but this is going to make a slow job even slower. And so as compared to ours GBM, which is one of the very popular models, H2O is willing to work with up to 65,000 factors. We have it running in-house on very large amounts of data, over 100 gigabytes, and we'd be happy for it to work on much more. And we're seeing 4x speeds are faster on a single node, and it does scale with the number of nodes in your system. And that's it. So I'm going to hand things over to Cliff, and he's going to talk about an implementation.
Okay, so I'm going to shift directions. Okay, so, oh, you mean on the implementation side here? Yeah, okay. So this algorithm came from Trevor Hasty in his book on elements of statistical learning. I think there's a whole section in the book on it, and in particular, I'll show you the page. I think Earl flopped that page up, which is what we've implemented. And so we'll get there. Okay, so the shift in direction I'm going to go here is I'm the systems implementer engineering guy and not the math guy. So I'm implementing the math that people say works well, and I figure out how to make it go fast. So what really is going on here is 0xData is building a thing we call H2O, which is this pure Java open source stuff. Here's the GitHub link. You can go download and play with the source code. And what it really is, it's a platform for doing math. So in particular, parallel and distributed math. And we're using it to do a lot of in-memory analytics. So GBM, but generalized linear modeling, random forest, logistic regression, there's a number of things, k-means. And the platform is drivable and from a number of different directions, including REST and JSON, which from the REST and JSON paradigm, you can get to R, which we'll demo here in a little while. R Studio, I'll drive some demos from that. From Excel, from Python, from a number of other languages. So it's a very general purpose way to get at this thing. And then the parallel and distributed part is basically as much memory and system and cores as you put together in a cluster. Okay, so what I'm going to talk about then is some notions of doing stuff with big data. So what is the notion of how do we talk about it? Then I get into distributed tree algorithms, for which GBM's one of them, and random forest is another, and there are others floating around. And then we'll get into specifics on GBMs on H2O and how fast and how long and so forth and so on. So the first thing we'll talk about here is big data. And how do I talk about big data? So H2O internally builds a thing we call a VEC. So this is this Java code I wrote up here. And a VEC is like, it's like a Java array, except it has more than 2 billion elements maybe. It's as many elements as fit in a long or in your cluster. And just fast random access to get things and to put things. And there's a notion of missing elements because a lot of the algorithms need that. And they can be variable size, have some other interesting features. And the vectors are, we collect them and we align them in memory in a way that fits the notions you have about like an R data frame, about looking at your data. So there's some pile of these vectors all striped through memory, and they're aligned on, they're aligned in the JVMs, but they're striped across the cluster. So any individual vector here might be bigger than what fits on one machine, but certainly the collection of all of it is. However, when we stripe it this way, we can get access to a row across at fast access for any one JVM for that one chunk of data. But the one JVM, while he can get at the other data, it's a network traffic overhead. So the goal here is to have each JVM work on data that's local to himself and describe what they're doing, the math they're doing in a way that's sort of natural and easy without thinking about the boundaries that are breaking the data up here. Because if I did that, I'll never get my algorithms written. So within these chunks of data, I have, or within these vectors, I break things up into chunks. That'll show up here in a little bit. A chunk is typically 1,000 to 1,000,000 elements. And it contains my raw data. Internal to a chunk, I do some sort of compression. The effect of the compression is typically my in-memory data is no bigger than the gzipped file on disk, and often smaller, sometimes 2 or 3x smaller. So I get a fair amount of compression here. And despite the compression, I can pull it out in a few clock cycles, generally faster than my memory can stream it in to the CPU. So the compression's essentially for free in that sense. Right? It didn't cost me anything to do the compression. And I win because I get more data. I can squeeze more data into RAM. Okay, so within the chunks, a CPU is going to work on a chunk. He's going to work on all the data across all his columns within a chunk. And another CPU is going to work on another chunk, and another chunk, and so on and so forth. And so pretty much I light up all the CPUs as I march through the data and do something with it. So this notion of a chunk shows up because it's my unit of parallel execution, parallel access. And then I'm not moving the data anywhere, and typically the codes move to the data, everyone runs their piece in parallel, and then they roll up results together, and that's what we're going to get to in here in a minute. But it's all about talking about what I'm doing within a chunk. This is the main core of the algorithm, and then there's a roll-up phase for the data between the CPUs and then across the clusters, rolling up to the top level where it's being driven. So to summarize, I've got a frame which is very similar to an R frame. It's a collection of vectors. The vectors can be billions of elements long. They're broken up into chunks, which are big enough that I can do some sort of efficient batch processing on a chunk. But a chunk might be 1,000 to 1,000,000 elements. And an element's conceptually a Java double, although it's actually, how it's stored in memory is up to the compression scheme. If I have a column full of booleans, it will be stored in memory as a bit set. And I don't think about it as a bit set. It's just happens to contain only 2 values. And when I say, get me the value, I get whatever the 2 choices are. And then I can talk about a row of all the elements of a vec going across. And my guarantee is that this will be efficient. If I talk about the same row on one CPU, I can march sideways through the data at essentially no cost. Okay, so within that taxonomy here, I have sort of 3 ways to look at the system. And the top easy level way is to say, I don't think about distribution coding at all. And this is using REST and JSON to drive whole algorithms. So I can go to the console, or I can go to my R console and say, please load this data set from S3 or HDFS or local disk or wherever it is. And the fact that it's being loaded in parallel across the cluster is not something I care about or I see. It's just going to get loaded that way, striped across the cluster. It's all invisible. It happens. It's done. Then I can say, run GBM or run GLM or do whatever, and we'll demo this here in a little bit. And I'll get an answer back. And in that sense, I'm just cycling the system like it's a black box for doing math. And it's very useful at that level. That's a good point. OK, so how many people here code or are interested in coding math at some level versus using it? So the coders, people who do coding for a living or were thinking about doing code for math. So like a third of the audience maybe. It's interesting. How many people here do math for a living and are interested in a black box that magically runs math faster? Aha. So I got fewer, several. Yeah, there's some scattered around. OK, that's very interesting. I might shift talks here. I went for the data science-y talk, and I have the systems engineering version. We can go into more detail if you want. OK, so this talk, much of what comes next is going to be how to do data parallel coding in a way that's sort of reasonably easy to look at. And in particular, it's going to be heavy on the MapReduce, but not your grandfather's MapReduce. So when I say MapReduce, I'm talking about nothing to do with Hadoop, but with the conceptually clean notion of map and reduce. So map takes as a function from my data to some value, and reduce takes pairs of those things, whatever they are, and folds them together pair by pair and gives me 1 where I used to have 2. So this particular map is conflating the types. So it's a little harder to see what the choices are, but it's just going to do the obvious sum of squares. And the map is taking some value, doing some function on it, and returning me something that might be of a different type. But this type matches this type, and the reduction takes pairs of these and folds them into 1. And then I say do all, and I've handed a vector. And this will run parallel and distributed across my cluster with no further work. So this piece of code just gives me sums of squares. And in fact, it will run at memory bandwidth speeds here. I can't actually make it run any faster. It's going to be milliseconds per gigabyte kind of speeds. But I can get more complicated in my inner loop. So let's look at that. So I can have state in particular. And in this case, The map is taking multiple inputs, however many inputs I want, and producing a this pointer. And he's updating in place in memory. So I'm showing, again, something fairly simple. It's the linear regression pass 1. But I can have something pretty complicated in here that I'm accumulating state on. And it's really in the this pointer. And the reduce is taking the this and the that and folding them together. So a map will run over a chunk for 1,000 or a million elements in parallel with all other CPUs running their maps over all their 1,000 to a million elements. And reduce will take pairs of those million elements and fold them together in a logarithmic tree rollup. Most of the reduces will happen within your node, but when you've done all the work on your node, they'll start going across the cluster, pair by pair over the network, until they roll the results back to where you started from. So here it is with the chunks more exposed. So here's my batching, where I can say for I equals 1 to the length of a chunk. So I've passed in chunks here instead of raw values. And then I fetched my double x and y out by calling chunk at and chunk at. And this is where my decompression happened. So this is under the hood. It's doing a bit set, bit vector lookup if that's what your data is stored at. And it's shift scale add or whatever the compression scheme of the moment is. And then you do the same map you had before, and the reduction's unchanged. So this is pretty efficient, actually. And this is just doing stride one access through memory, and so is that. x86 is really good at prefetching that. This will run at memory bandwidth speeds and saturate your CPUs and do the math all at one go. And because it's a batch thing, I can do work outside the loop if I have some interesting loop invariant stuff to pull out, and know that that extra work is not happening everywhere all the time for every row. It's happening once per chunk, which are already 1,000 to 1 or 1,000,000 to 1 reduced from the original work. So this is a pretty efficient way to write things if you can contemplate your code as a map and a reduce. All right, so I have more systems-y side on the kind of stuff you can do here. Let me back up a slide here and go back, and we'll poll the audience one more time. So I've shown some real basic stuff here, but I can get into more detail doing group bys and uniques across clusters and all kinds of cool things you can do in this paradigm in a very straightforward way. Because we're looking at GBM tonight, I'm going to turn over and head for GBM. But I can come back and talk about more of the kinds of things you can do in this paradigm that we're going to run like really fast across your cluster. So here's the algorithm. I think you saw this page before. This is Hasty, Tiptrani, and Friedman. It's an eye chart in some ways, but most of the math here is really cheap and easy, except this one. Fit a regression tree where you have millions or billions of rows. And what is the cost and time of building a regression tree? How do we make that go fast? So what I'm really going to talk about now is how I contemplate, think about a tree on data that's striped across a cluster. And what I really do is I take the nodes of a tree, the leaves of a tree, and assign every row to whichever node on the tree it happens to land in. If it was walked down the decision tree, it ended up on some node, some leaf of that tree. So I give it a number, and I assign a node to the number by making a giant set here, and for each row, I've set it to whatever node ID it landed on. And this is some temporary vector I've made. So by the way, this makes me a vector that's of size equal to the original guy, so it's a parallel temp, except because it's all full of zeros, it compresses really, really, really well. So it's essentially free. Cost me like almost nothing at all to make a zero vector of 1 billion elements. And then I make a pass over all the rows. So when I visit a row, it's at some node. I don't know which one. So the nodes are not visited in order, but the rows are visited in order. And because the rows are visited in order, I'm very efficient at touching my data. And then I'm going to do some work per row. And in particular, what I do is I grab histograms. So let's go look at what that turns into. So I have some initial tree here. And I've started all rows at node 0. And I've got some value of my predictor and some values of my response variable. And I'm trying to figure out how to split this tree up so I can make a prediction on my y based on just x's, right? So I make a sweep over all the data, and I accumulate sums and sums of squares, and I get average and variance out. OK, fine. Using that information, I'm looking for a split decision. And one of the things I didn't say here is I've done the histogram building is built on x's as they're broken out by different choices. And I go through the same decision that you saw with Earl, where I walk down the line saying, if x is less than 0, less than 1, less than 2, less than 3, here's my error and my variance as I walk through, right? Based on that, I come up with some decision, and I decide to encode it in the tree. The tree is just a POJO, a plain old Java object. So I didn't do anything special about the tree except define a Java object that looks like a tree and looks like a Java tree object, whatever. And I give it a decision. Hey, if you're column X and if you're 1.5, go left, else go right. And then I make another pass over all the nodes. And when I make the pass, I pick each node and apply it to this decision, and it goes left or right. And I assign a new node ID to it. And then I bin it again, according to which piece it landed. So I end up with a histogram for every node in the tree, and whatever rows landed on that histogram pile in, and they get an average and a variance for that particular node. And then, looking again at this set of data, this is my small data. It's only 2 right now. It's 2 elements of the tree. Even though there might be a billion rows in each set, I end up with 2 things, and I look at each one, split it or not. Looks pretty clear that node 2 doesn't need to be split anymore. It's got a good decision. Variance is very low. If I just predict 1.2, I'm like spot on. Whereas the other guy is pretty big variance. So maybe I decide to like chop this guy off. But I'll keep going with the other guys, make another pass through all my data, and decide to split it again and get a different predictor value for the leaves on that. And so on as I add layers to the tree. So what really happens is that I need a pass over my data for each layer in the tree. But every pass is fully data parallel. So as I add more data, if I add more nodes, I divide the work of the data by the nodes that I've added, and I keep dividing the work per layer to get my speed up, right? So sequentially, I'm going down, but each sequential pass is as fast as I have nodes to divide the data up amongst. Okay, yeah, it's just what I said. Each pass is a layer in the tree, but I'm building them one at a time here. This is a short eye chart form of the pass. I'll touch it real quick, and then we'll move on here. So I have a map call over my data, and so I've just made a pass thing, which comes from MapReduce task. He's got some node IDs. He's pulling out of one of the chunks here is my data. So all my columns are my chunks array, so my node IDs is temps. And I'm rolling over all my rows, grabbing out the length of the rows there. I pull a node ID out for this row, and then I go ahead and make sure there's a histogram. Not all chunks will see all nodes in all trees. Some chunks will all like land here or land there. So I'm lazily producing my histograms. But once I got a histogram, I go ahead and do whatever accumulate does, which in this example is going to compute, bin my predictor, and then compute sums and sums of squares for each of the different pieces, so I can make a decision later. And I just say do all on my data frame and my extra temp variables. And this is running now across the cluster. And I'll show you examples which look very similar to this straight out of the H2O code base here if people are interested. But this is pretty dang close to what the actual codes looks like.
Cliff and I started this company after finding no tools after staring at an R screen for more than 12 hours or 16 hours myself and trying to build simulations that took weeks at length. I mean, all science has been now the lowest common denominator is data science. Data collection is cheap. Data science is the only science left. So we want to build great tools and make them available in Apache V2 so you can embed it, use it, plug it into R. The future looks like it'll just be a R wrapper, basically another package that implements cool packages in R, so you guys can access it from R and Python and Excel. We are not yet another big data startup trying to do something cool while it's popular. We are going to be around. We're going to build this math library till we find the right math for our time. I think one of the things missing in this whole discussion is GBM is the cutting edge algorithm, and that's why we're starting there. But what if the math that's needed to solve our big data problems is missing? And that's kind of where we want to encourage the audience to be part of this. GBM didn't come out of the blue. We asked the audience when we were building random forests, what would they like to see in decision trees? That was 4 months ago, so the last 3 months was building GBM. And the next 3 months could be the algorithm you guys want. So please be part of the overall conversation. And it's a product's not complete without the community behind it. So with that, I'll give it back to Cliff here.
The tar file that comes with the tar file that came here comes with H2O. You download it from the web and you get it. You're going to install a package. I'll come on this side over here. Da, da, da. And we're going to do.
How's the font? Should we increase the font?
People can see this in the back? Sort of, kind of. I think 1 or 2 font size increases wouldn't hurt anybody. Does that look all right? All right, so yeah, that's when we go on here. So there's a couple steps to install. Find your package, load the dependent packages. So the main package pulls in some other stuff we need. Part of the things we're doing here is like our curl, and this is where we're gonna use the REST and JSON to talk to and from a cluster. So what you saw on the background was that we have a cluster running up in our lab, and so I was getting a VPN connection to it. So we can show some big data being driven by R. To the back end. So it should be, so here's the IP address from our back-end cluster as forwarded through VPN. Should be 161, yeah? 60024. The port, okay. Yeah. Yep. Go. And the magic of VPN. Bam. Okay, it's up and running. And this says we're connected to this cluster. So this is the small data demo. Uh-huh. Uh-oh. Okay. Oh, right. Yeah. All right, now try this. No, you didn't do the yeah, didn't do the initial launch. Yeah. Yes, I am. One of the init steps needs the local thing. All right, where's Angie? We're gonna do this locally from my laptop here in a second. Yeah. 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 Isn't this the demo? Oh no. No, where's the data? All right, you gotta do, yeah, you can't do it that way. You want to do this from local here?
So I guess we can import data from this data.
Yeah. Now you need the local H2O. And then I think it says path. And HDFS colon something. So we have an HDFS at our office that we test against. We can load data locally. This one is the cluster is running, I think it's Airlines All. The cluster is running at the office as well as the Hadoop server, but they don't have to be co-located, although they can be. H2O does all its own internal clustering. And so we don't require Hadoop. We work fine on S3. We work fine on local data sets. You can run a one-node H2O cluster on your laptop for nothing more than java-jar, h2o.jar, and it'll come up and be ready to go. And in that sense, it's a very fast way to run GBM. Okay, so this is coming from the cluster now. And here is the cluster. It's a 4-node cluster of 200 gigabyte machines. So it's actually a pretty big cluster. And I think there's going to be, we're pulling in the data set. Okay, so R has asked for this data set to load from RStudio, and we're pulling in. This is a couple gigabytes worth of data, like 12 or something.
It's all 120 million rows.
Okay. And this will take a minute or two. And if we look, there's some system load, and some CPUs are busy, and some memory, free memory sizes will go up and down according to GC cycles. And the data is piling in, and getting spread around the cluster. It's on the VNC tab. Yeah. So somebody's stuck doing I/O. It's however fast HDFS will hand us data. I don't know. Maybe you're done. You're on the wrong. Oh, you're done. Go find what RStudio says. RStudio says okay. So you loaded 12 gigs. You want to do like a head of that? And so this went into the H2O cluster and said, give me the first 6, 7 rows of the airline data set. So 120 million rows. Run a summary and let's take a look. So summary is going to compute more interesting stats over the whole data set. And we can, oh, there it is. So 120 million rows. You got first quartile, median, mean, max quartile. Yeah. So okay, here we have a web GUI that does JSON in and out, or pretty prints the web. Pretty prints the JSON as HTML. So you can drive it this way, and which is really convenient for point-click shooting on things. And then if you hit the JSON button in the upper right corner, you'll get this all piled out as piles of JSON. So it's convenient to drive it this way and look at the JSON if you're making a script that's using REST and JSON to drive things. But this was 120 million rows, and we've broken out like histograms of which column is this? Oh, okay. This is the carrier. So 12% of all flights were done by American Airlines in the last 20 years, and here's Delta at like 13%, and whoever else. This is like Northwest U.S. Airways, maybe in Northwest. So this particular data set is the accumulation of flights for the last 20 years, including their on-time behavior. And one of the fun things you can do with this is go do a prediction on the on-time behavior of flights and see if you can figure out who's fast and who's slow and wide. Okay, there's the last zillion rows. Yeah. You want is departure delayed is on the screen there. Do you want to drive it from here? Yeah, just do all for now because it's going to be a lot easier, and it won't be a realistic model. Okay. So the easier thing to do here, so if you're doing, so the particular thing about the airline data set is that they also included with the departure delayed or not a bunch of information about why it was delayed. And so if you're building a predictive model and you have information telling you why it was delayed, then you were delayed. So if you're predicting delay, you just have to look over the next column and see that, oh, I have a delay code, so therefore I'm delayed, right? So it makes it an unrealistic model. So the goal here is we're going to try to look at predicting a model where we're predicting on-time behavior based on things that are not available to you 24 hours in advance, right? So don't get to cheat and look for the delay code, but try and figure out why you were delayed or not. So Shree's stepping through the different delay codes here: diverted, canceled codes. You can have taxi. That's probably in there. Maybe it's probably okay. Sure. I don't know. I don't think that one makes a difference. Oops. It's wrong keyboard. It's a Mac guy on a Windows box, as opposed to the Windows guy on the Mac box. I think some more CRS times. I think that's it. And scroll down. Yeah, you're good. Okay, so number of trees you want to build, the max depth of the trees, minimum observations on a leaf, the amount of binning points you're going to split at, the learn rate, which is pretty high here compared to what people do, but we're trying to get a demo on some length of time. So It flips to this mode, and then it starts lighting up tree cores. So you want to flip to the VNC session here for a second here? Okay, so yeah. So here I am running data parallel across 12 gigs of data, 120 million rows of data. And in the little like doinks, that's stopping to roll up the data and declare a tree split and go to the next one. And every 5 or 6 of these, maybe it's like 8 or 9 of these, you get another tree level done. There's some number of these passes here to make a tree. I don't have the right count of them. But it's going to be building trees as we go here. And we've got some trees built. And because the shrinkage is there as 0.1, you can imagine that means that the predictive quality of a tree is reduced by 90%. So each tree only moves the bar just a little bit away from the median to try and get a better and better prediction. And the reason for that shrinkage is to avoid overfitting, but it also means you have a lot of trees to get a reasonable fit. So in the beginning, we pile on trees, the fit's pretty bad, and we're slowly creeping in on it. And of course, the refresh is like wiping the screen down, and you can't shrink the font. But you can see it's still pounding away here and lighting up all the cores. I guess these are 32-way machines. Yeah, it's 4 times 32, so 128 cores, like going to town.
The entire operation on the hardware front was less than 30 grand, so it's not a very expensive machinery, but the state of art today, probably one minus today's machineries. So these are not expensive. These are Linux Intel boxes. And typically we find our customers use one of those boxes in hope of getting their GBM go faster, but it usually lights up one core. And Tom's a perf bar artist, so we decided to use perf bar to demo.
I think that's the big pieces of the demo. Why don't I take questions from people for a while here? People too excited about the perf bar going up and down.
Final questions? How big was the data set again?
12 gigs on disk. In RAM, maybe you can open another tab, show the data in RAM.
So essentially, so airline data set is a popular data set for playing in the space, where basically you're trying to use all 20 years takeoff and landing flights, and that's about 120 million journeys, our journeys, and basically this data set has to compress 5 gigs, but really 12 gigs on disk. People usually sample that data set so they can run GBM, they can run GLM. On this platform, it takes 5 seconds to finish a GLM on an entire data set, logistic regression, on all 700. I think it's roughly 700 categorical columns when it expands. So in terms of factor, so it's a pretty high-speed system that Cliff and the gang have put together. So we would love. I mean, this is available for download on our main website. It's open source, and we want people to use it. It's almost like G8 as of today, and so you should try and use the product. GBM will show up in the browser. I think if you had a local host, the demo would have worked on our studio as well.
Yeah, I don't have a local JVM running, but I test and play with RStudio, just running my H2O on my laptop.
Any other questions?
Yeah.
I saw mention that you also parallelized random forest calculation.
Yeah, random forest is designed to be parallelized, and we parallelized it in the obvious way. So you just run the trees in parallel. You build the trees in parallel. They're all independent.
Have you done comparison on the same data set with your parallelization of random forest versus GBM in runtime and in accuracy?
I have not, because GBM's too new.
It's what I asked Earl to do at 4 p.m. today, and he said next meetup.
My experiences have shown increased accuracy, and it's slower.
For GBM.
For
GBM, but more accuracy and slower. Yeah, RF like tops out at some count of trees, and adding more trees doesn't seem to help it.
RF has some very neat tricks, but the thing that any boosting algorithm is going to get you is it weights where you're wrong.
Yeah.
And RF is fundamentally going to be unable to that costs you the iterative nature.
Yeah.
But on big data, is it possible that random forest could get you really good results?
Absolutely.
So yeah, I think so. The last Thursday's talk where Trevor, by the way, major kudos to the Stanford Math team, which works very closely with us, Dr. Boyd, Trevor Hasty, and Rob Kipshirani. Trevor basically corrected and made us build the exact textbook algorithm that Cliff has for you guys. And I mean, finally got on stage, and till it was actually the page number 387 on ELS third edition book, he was not satisfied. And so it was done and approved. So in that sense of it, major kudos to the team that's not here as well, but it's our advisors who in Stanford have done a terrific job. But with that, I think we're running short of time. I want to recover. Yep. And thank you.